Hello again. So we will continue our discussion of the dynamic optimization, and this time we will consider the case of a discrete time, and for that we mostly use the Lagrangian multiplier tool for optimization. Again, our focus will be on the application side of optimization problem, and in this case we will consider the case of an individual household, and we will use a slightly different formulation for this problem. What we discussed for the continuous time case is what we call the decentralized comparative equilibrium, and what we will discuss over here is what we call the social planner problem, and in which a hypothetical social planner who is a fictional entity who chooses allocation for every agent in the economy that maximizes the social welfare function for everybody subject to certain constraint. So there are certain assumptions for that. One is that the economy is populated by a large number of identical, infinitely lived households and agents, and these agents consume and save in physical capital, supply a unit of labor to each period. Population grows at a rate n. Households get flow utility from consumption and discount the future by a discount rate beta. So again, this discount rate is a parallel version of e raised to the power rho when we discussed the continuous time case. And firms produce output using capital and labor and capital, and constant to scale production function, and firms are owned by the household. So let's assume the production takes the form of a Cobb Douglas, which is in this form, and let's also assume the same utility function for consumer as we used before, which is this form. And output must be consumed or used as an investment in the new capital goods. So we will have the aggregate resource constraint for the economy. That would be YT, total output produced in an economy. It has to be either consumed or invested for future capital stock. And from there, we will get the law of motion of capital, talking about the investment. So the capital stock tomorrow, what this equation, which we call the equation of motion of capital, it says that the capital stock tomorrow is whatever capital stock we have today, but part of that capital stock would be lost because of some depreciation, and plus whatever investment we decided to make today. So this is how evolution of capital stock will take place. So now we can set up our social planner problem, and the social planner problem would look like this, where we have to maximize consumption and capital stock tomorrow. These are our choice variables. We will choose consumption and capital stock for tomorrow, and such that we will maximize the discounted lifetime utility for the consumer, and subject to the constraint. The constraint would be again this, but where we have to substitute the value of investment from here. So our equation would look like this. And what we can do is that we can substitute the value of production function yt from here as well. So this will give us the expression of kt plus 1 equals to kt alpha nt raised by 1 minus alpha minus et plus 1 minus delta kt. So we have now the objective function, the constraint, and we can proceed to set up a Lagrangian for this optimization problem. The optimization problem for social planner under discrete time case would look like this. We call that a current value Lagrangian, and where this beta discount factor gets multiplied with this overall optimization equation. If we just multiply beta with the utility function, that's what we call the present value, but and the end result is same for both cases, so we will proceed with this current value Lagrangian formulation. So this is what we have over here, where we have set up a Lagrangian where the consumer will maximize utility and discounted lifetime utility subject to resource constraint. So this social planner will maximize the utility of a consumer subject to this economy's resource constraint. Again, we will draw the first order conditions. In this case, the first order conditions will be drawn with respect to Ct and Kt plus 1. Notice we will not and lambda t. Notice we will not do first order condition with respect to Kt because Kt would be given in the current period, or we will call Kt as capital as a predetermined variable. So in the current period, the social planner will choose consumption Kt plus 1, next period capital stock, and the other first FOC would be with respect to the Lagrange multiplier. Okay, so let's just proceed with those FOCs. So what we get over here when we differentiate with respect to Ct is that this beta t will come as it is, and then this differential of this function would be c raised by minus theta, but we have ct over here as well, so there would be a minus 1, and then that will get multiplied with lambda t, so we will get this expression. We can simplify that a little bit more, and this will give us this expression because beta t, the value of beta discount factor, is between 0 and 1, so this cannot be equal to 0. It means this would be equals to this thing. The expectation operator will be dropped out because in the current period everything would be known, so we can drop out the expectation operator as well. Let's move on towards the second FOC with respect to the lambda t. This whole equation will come as it is over here, and then we move on to the third FOC, which is slightly tricky. Notice that the Kt plus 1 actually appears on two spots over here. First, it appears over here that when we will differentiate at time t, it will be lambda t, then minus 1, and beta t, this will come over here. But when we will iterate it in the next period, this will become Kt plus 1, and so does this. So we will have at time t plus 1 these two expressions that we need to differentiate. So let's just iterate it to the next period. Everything, wherever there is a t, it would become t plus 1. So we will have beta raised to power t plus 1, and then we will differentiate this expression because they would be t plus 1, so we'll differentiate that, and next this will get differentiated. So this we will have a third FOC. So we have to now solve these FOCs simultaneously, and we'll reach to the Euler equation. Basically what we have to do is to remove those Lagrangian multipliers from here. So I can write this equation in this form where what I did is that I just wrote, instead of beta raised by t plus 1, I wrote beta raised by t and then beta. In this way, I can cancel out beta t from both sides. And the next step that I have to do is then I'll substitute the value of lambda t and lambda t plus 1 from this expression. If I know if c lambda t is equals to ct raised by minus theta, then lambda t plus 1 would be equals to ct plus 1 raised to the power minus theta. So when I substitute that in this step, we are just cancelling out. In the next step, we will substitute the value of lambda t and lambda t plus 1 in this equation. So with here, we are going to substitute this lambda t and lambda t plus 1 in this equation. So when we substitute those lambda t and lambda t plus 1 in this equation, we get this Euler equation for the discrete time case. The only difference is in this case we have, other than consumption, we have t plus 1 capital and labor as well in this discrete time case. Again, from there onward, we will use some other methods to solve those set of difference equations to reach to a solution for consumption. The end goal is again to find the time path, to find an equation which can give us a time path of consumption.